Hello, everybody, and welcome to Physics Rich. Today, we are starting the very basic lecture on fluid mechanics. Guys, behind me, you can see a beautiful rendition of everything that you will study in fluid mechanics. You can see some static fluids over here. Fluid statics is going to be our first subtopic in fluid mechanics. You can see the Bernoulli's equation written over here. That will be the next thing. This is the aerofoil. This is an airplane flying which uses the concept of aerofoil. And you can see a boat rowing on the surface of the water, which also tells us about viscosity, and this nice beautiful sphere which is kept on the surface of water because of surface tension. So these are all the topics that will be covered in the chapter of fluid dynamics, and each of these topics are very important. They are all very important because time and again we have seen that all the exams have been asking questions on these topics. We know that this is an easy chapter. There's nothing to worry about it. This is an easy chapter. If you work slightly bit upon it, you will get very good marks. It's a high weighted chapter in JEE Mains and Advanced both, and of course NEET. There were 16 questions in the January attempt of 2025. There were 10 questions in April attempt overall. All right, not just one exam. It's not possible for one exam to have 16 questions from one chapter. So, two questions in JEE Advanced, which is 5% of all of physics, and there was one question in NEET. This lecture is going to be useful for the aspirants of all types. You will all be able to benefit from it. You can be a NEET aspirant, you can be a JEE aspirant, whoever you are, even if you are not intending to write any of these exams, if you are just preparing for your school exams, even then this lecture is going to be very helpful to you all. We will be studying about fluid statics in this unit. So first we'll start with fluid statics, we'll move on to fluid dynamics, and then we will take it off further into viscosity and surface tension. So let's begin today's lecture with understanding what fluid statics is. So guys, fluid statics is defined for all the fluids that remain at rest with respect to a container. What I mean to say is that if there is a simple, you can see a table over here, all right, this is a table which is kept on a floor, all right, this is a floor, and if I have a container over here and if I fill some fluid in it, this is a static fluid. Now, if I take this table, okay, if I take this table and I put it behind a truck, okay, this is a truck and this truck is now moving. All right, this truck is now moving, and you see that this fluid is kept inside of a truck. Apparently, it seems that the truck is moving, and due to which the fluid also seems to be moving. But my dear students, this will still be counted as to be studied under the purview of fluid statics because the fluid is remaining at rest with respect to the container. However, if I poke a hole over here, all right, if I poke a hole over here, fluid will start to flow, it will start to pour outside, and then we will not be talking about fluid statics, then we will be talking about fluid dynamics, because now the fluid is pouring out, it is not at rest with respect to the container will see some fluid coming out of it. All right, guys, so this is a simple distinction between fluid statics and fluid dynamics. So guys, this chapter mainly deals with liquids. All right, I mean, they do call it fluid mechanics, and fluids are basically substances that can flow, which means that they are both liquids and gases. Gases are also considered fluids, but in this chapter we will not deal with gases. For gases, we will go to thermodynamics and KTG, which is the next chapter, and then we will study them as in gases in detail. So in this chapter, we will be majorly focusing only on liquids. And in this unit of fluid statics, we will be talking about liquids at rest. Now you see guys, there are multiple phases of matter. You know that there are solids, there are liquids, and there are gases. These are the most common phases of matter. There are three most common phases of matter: solids, liquids, and gases. There is something called plasma. There is also something called Bose-Einstein condensate. These are also different phases of matter. Plasma is something that you find on the sun. But plasma and Bose-Einstein condensate are both not a part of our syllabus. So if at all somebody asks you how many phases of matter are there, you can gladly say that in my syllabus, I am studying in grade 11th and 12th. In my syllabus, I only know three phases. I do not know about plasma and I do not know about Bose-Einstein condensate, and there's nothing wrong in saying that because it is not in your syllabus. If you don't know about it, no problem. You will go to your pure sciences when you study pure sciences, when you go to your maybe MSc courses in physics in IIT, then you will study about Bose-Einstein condensate and plasma, especially if you study about particle physics. Okay. Fluid dynamics, however, fluid dynamics, and what I mean by fluid dynamics is flowing fluids. And I would rather say even static fluids. They deal with something called ideal fluids. Okay. So no gases, no Bose-Einstein condensate, no plasma, no solids, just ideal fluids. All right. We will be only discussing about ideal fluids. And like I was saying, guys, a while ago, I was telling you that materials that they have the ability to flow are called fluids. All right. And that makes liquids and gases as fluids. Now, what is the distinction between liquids and gases? And I'm sure you must have studied about these when you were children, when you were in your junior grades, maybe grade 7th or 8th maybe. You must have studied that the molecules of gases are far apart from each other and they move in all possible directions, and the gap between the molecules is very large compared to the size of the molecules. However, in liquids that is not the case. They do not have molecules that are very far apart from each other. They have a gap which is comparable to the molecular sizes. They do not go too far away from each other. The molecules of the liquid, they do not go too far away from each other. But in grade 11th, the most important part that you must understand about liquids is that liquids do not have a fixed shape. And I'm sure this is also something that you have studied in your junior classes, that they do not have a fixed shape, but they do have a fixed size. Now in grade 11th, we understand how. So let's say you're going on a picnic and you decide to get some water with you. Now, this water is something that you will fill in maybe a can or a camphor, but you do realize that that can or a camphor is going to take a lot of space in the vehicle that you will use to go to the picnic. Perhaps it's your own car. Now, you will have to put it somewhere. What you cannot do is you cannot squeeze that camphor and store the liquid in a squeezed small vessel, because the size, the volume of the water that you are about to take is not going to change. It is not compressible. And when I say that liquids have a fixed volume, they have a nearly fixed volume, what it means is that for all practical purposes, liquids are incompressible. You cannot compress them, and of course when you compress anything, its density changes. You cannot change its density by simply compressing it, unless we are talking about very tiny minute values where we assume the liquids to be very compressible to a very small extent, which is still practically possible. As in, when you jump into the water of the ocean, okay, I mean, don't do that, but I'm just telling you that if at all you jump into the water of the ocean, you go very much deep inside, you will find that the density of the water deep inside is slightly more than the density of the water on the surface. And that's only because the water underneath is highly compressed by the water which is above it. All right. So in practical sense, yes, liquids are compressible, but for the purpose of our study, we will assume that the density of liquids do not change unless it is specified in the question that you're doing. Okay, so liquids have a fixed volume, but what they do not have is a fixed shape. Let's get back to the camphor or the container or the can that you were taking to the picnic. Where did you take this water from? Perhaps some water dispensing machine, perhaps from another bottle. All right. I am sure that the water that was there in the dispensing machine did not have the same shape as the can that you're taking. And it had a different shape earlier, and later on it had a different shape. So you can clearly see that the shape of the liquid changed. So why did the shape of the liquid change? In grade 11th, we study about something called shear force. And guys, the true reason is that ideal liquids, the liquids that do not have any viscosity, they cannot handle shear force. If you apply shear force on them, they just change their shape. And that's the reason why ideal liquids cannot have a fixed shape. They will take the shape of the container that you will put them in. But what about gases? Gases, they do not have a fixed shape and they do not have a fixed volume either. All right. On gases, you can say that a gas will occupy the entire space of the container that you put it in. Okay. There is gas in this room in which I am currently recording this video. And if at all I were to put some perfume in it, speaking of which, let us make the room a little better. So now you see I sprayed it over here, but if I move over here, I can still smell the perfume. Okay, because it's gas. Gases will just go to the entire room. If I put the perfume on one side, if you were to be in my room right now, you will feel that the perfume can be smelled from every corner of the room. So gases do not have a fixed shape and they definitely do not have a fixed volume either. And what about solids? Solids have a fixed volume and a fixed shape. We consider solids to be practically incompressible and their shape can also not easily be changed unless you apply a large amount of shear force on them. Volume, however, guys, let's talk about volume. What exactly is volume? It's the amount of space that is occupied by any material. You have studied about volume in your junior classes, especially in mathematics, in the chapter of surface areas and volumes. Some people call it mensuration. You have studied that there is a volume that is occupied by a cube. If the cube has a side A, it has a volume of A cube. If it has if it's a cuboid and it has three different dimensions, there is length, breadth, and height, then the volume becomes LBH. If it's a cylinder, then the volume becomes pi r square h. You have studied all these things in your junior classes. And we understand that volume is actually the space which is occupied by any material. And we measure volume in the units of meter cube. And like I said, length, breadth, height. There are three dimensions of length, which is why the dimensions of volume are L cube. Now, over here, I have written some conversion units which are useful. A meter cube is the same as 1,000 liters. You must have seen a meter cube. I don't know if you've seen it, but a lot of places, a lot of houses, they have tanks of water on top of the roof to store water, and those usually have a capacity of a meter cube. It contains 1,000 liters of water. If you have 1,000 liters of bottles, like bottles of 1,000 ml of water, like 1 liter water, you can pour 1,000 of those into that large tank and then it will become full. So a liter has 1,000 ml. You have to remember this, guys. A liter has 1,000 ml and a meter cube has 1,000 liters. ml, cc, and centimeter cube, they are all the same things. Okay, they are all the same things. 1 ml, 1 cc, 1 centimeter cube, they are basically practically the same things. And certain times you will find a unit called a decimeter cube, and a decimeter cube is also the same thing as a liter. All right. So you have to remember all these things. Now let's talk about density. What is density? Density is basically mass per unit volume. Now, I need you to understand density very nicely. You can see that if in a given volume I am able to put a large amount of mass, then that substance must be having a large amount of density. For example, if I have a small box, and if I try to fill in cotton in there, how much cotton do you think I will be able to put? Perhaps not too much, right? Because the density of cotton is actually quite less, which means that the amount of mass that I will be able to push inside a small box of cotton is, well, not too much, which means that density of the cotton is less. But if I were to start filling in powdered iron inside of it, okay, that iron which is powdered, I will start pouring that powdered iron inside. There will be a large amount of mass of the iron that will be filled inside the box. So you can say that for the same volume, cotton occupies, we can say it has less mass, and if for the same volume you put iron, then iron will have a large amount of mass. And that's because density is an inherent property of materials. Iron has a different density, copper has a different density, and perhaps lead has a very high density. All right, osmium is said to have the highest of densities of all possible metals. And how do we define this? We define this by simply doing mass per unit volume. And we have the dimensions of density as ml minus 3. Density is m by v. This is the most commonly used symbol, which is rho. It's measured in kg per meter cube and also gram per centimeter cube. The kg per meter cube is the SI unit, and the gram per centimeter cube is the CGS unit of density. And a gram per centimeter cube is the same thing as 1000 kg per meter cube. If you're wondering how did I get this, then you should understand that 1 meter is actually equal to 100 centimeter. All right? Or rather, I should say it's equal to 10 to the power 2 centimeter. And if I cube on both sides, if I cube on either sides, then I get 1 meter cube is equal to 10 squared to the power 3 centimeter cube. And that is 10 to the power 6 centimeter cube. All right? All right. And also I can say that 1 kg is equals to 10 to the power 3 grams. All right. Now, if you take the ratio of these things, if you take the ratio, if you assume that this is 1 and if you assume that this is 2 and you divide 1 with 2, you'll get 1 kg upon a meter cube is equals to 10 to the power 3 g upon 10 to the power 6 centimeter cube. From here you will see that it will lead to a 10 to the power 3. It will lead to a 10 to the power 3, which you can then cross multiply onto this side. Okay? And that's how you get a gram per centimeter cube equals to 10 to the power 3 kg per meter cube. All right, guys. So this is how I found the correct correlation. And I encourage you all to do this yourself. I mean, it's actually always better to try to derive these things by yourself. That way you will remember them even better. Remember the density of water. It's one of the most important data to remember in this chapter. The density of water is 1000 kg per meter cube, and it is measured at 4 degrees and assumed to be constant. Again, the density of water can be varied. In practicality, yes, it can be varied, but it cannot be varied so much that it affects our calculations, which is why we assume that the density of water is either 1000 kg per meter cube or the same thing as 1 gram per centimeter cube or the same thing as 1 gram per cc or 1 kg per liter. All these are the densities of water and they are all the same values with different units. All right. I hope all this is clear up until now. Nothing confusing. And guys, if you ever have any doubts related to whatever we have studied, don't forget to put that in the comments. I will try my best to answer all the doubts that you get. Relative density. This is a relatively new term. Now, relative density it's defined as the ratio of density of a material to the density of a standard material, which is usually liquid water. RD is short for relative density. How do you define that? You take the density of the material and you divide it by the density of the reference material. As you can see that this is a ratio. It's a ratio. And because the numerator and the denominator have these similar type of physical quantities, that's why this is a dimensionless ratio. Okay, so RD does not have any dimensions and it also does not have any units. It neither has dimensions nor does it have units. Let's say that there was some oil that had a density of 900 kg per meter cube. We're assuming that this is some oil. We don't know what this is exactly. We're just assuming that some oil has a density of 900 kg per meter cube. Its relative density with respect to water, H2O means water, would be just simply 0.9. Please mind that I have not used any units and any dimensions. Then comes another physical quantity which is called specific gravity. Now, specific gravity is a type of relative density. We have just studied about what relative density is. It's the ratio of two densities of material and reference. And when we take the reference to be water, then specific gravity is what you call the relative density. Sg is the same as Rd when water is the reference material. Okay? And this is again one more thing which you have to remember. I hope you all can see it, that the specific gravity of mercury is 13.6. Again, it has no units and it has no dimensions. But if I were to ask you what is the density of mercury based upon this data, then you would say that the density of mercury, Hg is the symbol of mercury, okay? And that will be equal to, this is 13.6 times heavier than water. Heavier than water. So either you can say that this is 13.6 times 10 to the power 3 kg per meter cube. Okay, either you say it's 13.6 times 10 to the power 3 kg per meter cube, or you could just say that it has a density of 13.6 grams per centimeter cube, because the density of water is 1 gram per centimeter cube. Okay, all right, I hope this is easy to understand up until this point. Now we move on to something called ideal fluids. So guys, we have been talking about what ideal fluids are. Now it's the time that we exactly define what they are. Ideal fluids have a few properties. They are incompressible. And by incompressibility, what I mean to say that they have a constant density. You cannot change the density of an ideal fluid. It's true that ideal fluids are hypothetical substances. They do not exist in reality, but for the purpose of our study, we only take ideal fluids. And you cannot change the density of ideal fluids. They have a constant density. They are incompressible. Their volume remains constant and their mass also remains constant. This is the next property. It's called inviscidity. Or you could also say that ideal fluids are non-viscous. Okay? You could also write that they are non-viscous. They are non-viscous, which means that there is no viscosity. And what exactly is viscosity? Viscosity is fluid friction. It's the friction that exists in between the layers, hypothetical layers of fluids. So there is no friction and there is no sliding, there is no loss of energy because of friction in between fluid layers. So that means inviscidity. So the fluids are non-viscous. Then we speak of something called streamlined flow and also the fact that the fluid flow is irrotational. Now we will discuss about these more in fluid dynamics when we will be studying the next subtopic of fluid mechanics, which is fluid dynamics. And you will notice this kind of a diagram happening a lot more in fluid dynamics. You can see that there are certain vortexes that are forming. This fluid is trying to rotate. We don't want the fluid to rotate. That's what happens when we study fluid dynamics. Okay. And we also want the fluid to be streamlined, as in we want them to flow along these neat lines. Again, like I said, we will discuss a lot more about these when we will study fluid dynamics. Now comes the most important idea, which is pressure. Okay, pressure is technically where this chapter truly begins. If you already know about everything basic that we have studied up until now, great, absolutely great. I would pin this point in the video so that you can start directly from pressure. This is where the chapter truly begins. Pressure is defined as the normal force acting on a surface area. Pressure is basically the distribution of normal force on a given area. Now, pressure is actually a scalar quantity and it is defined as the thrust force divided by a unit amount of area. You can also write it as F perpendicular divided by area. If you notice over here, I have taken the magnitude of this F perpendicular vector. F perpendicular is the thrust force. It's the component of the force which is perpendicular to the area. Now, you can see that there is this person over here. We can only see the hands of this person and he's trying to maybe do some push-ups. Okay. You can see that there are these 3 points that I have tried to show in this picture, and the yellow colored arrows represent the yellow colored arrows. You can see that they are pointing downwards. These are the forces that the man is trying to apply on the surface. You can say that these 3 forces can definitely be different. Okay, but you can also see that there is a white colored arrow which is along the surface. So the net force because of this man on the surface may not exactly be perpendicular. It may be somewhere slanted to the perpendicular to the surface. It can be somewhere over here, but we are not concerned with that force. We are only concerned with the perpendicular force. All right? And that perpendicular force divided by whatever area it's acting upon is going to be the pressure. So you can see over here that these arrows that are pointing downwards, these arrows are basically representing forces. Okay? Pressure does not really have a direction. Okay? Pressure is a scalar quantity. It does not have a direction. But pressure acts in such a way that it causes a certain force to act. Now, if a pressure because of this finger is P1, then the force acting downwards will be P1A, where A is the small area on which this pressure is acting. Similarly, this will be P2A and then there will be P3A. P1, P2, P3 being the respective 3 different pressures at 3 different points because of this man doing push-ups. Okay, where A is the area that I've assumed to be the same and P1A is the force acting due to the pressure because of the contact that this man has at this point. Now, if you look at this fluid, in this fluid, the pressure arrows are everywhere. If I remove this image, you'll be able to see better. The pressure arrows are actually everywhere. Okay. Now, if I put this fluid over here, it makes no exact difference. If I just put it over here, then you will see that at this point in the fluid, if I go inside of this fluid at this point, I will see that the forces that will be present over here will be in all directions. Depends upon the area that I am putting inside. If I take a tiny area and I put it like this, then the fluid will push the area like this. Okay, it will push the area like this. If I put it like this, the fluid will push the area like that. If I put it like this, then the fluid will push the area like this. It depends upon the orientation of the area that I'm putting, and fluid will try to push the area perpendicular to it. All right, pressure will always apply a force perpendicular to the area. It's the area, it's actually the orientation of the area that decides where will be the force. All right, so pressure does not really have a direction. Pressure simply is the distribution of the force. So it does not have a direction. It's a scalar quantity and what you actually call it is an isotropic quantity. What is the meaning of isotropic? The word iso means same, and the word tropic means directionally. So it means that it's it's the same, it's distributed the same way in all the directions. So isotropic, tropic means directionally and iso means the same. So same direction, it means it is distributed in the same way in all the directions. Okay, at a given point you will see that the force will be acting in all the directions because pressure is an isotropic quantity. Okay, so pressure acts at a point. All right, pressure acts at a point and not along a direction. We measure it in pascals, and a pascal is the same thing as a Newton per meter square. Now you see guys that there are multiple ways that I can actually explain pressure to you. Now you look at me, you see I'm a big guy. I weigh something around 150 pounds maybe. Okay, not so big maybe. But yeah, I weigh decently, and if I were to wear shoes, all right, and accidentally step on your toes, it would hurt. Definitely it would hurt. But imagine that there is, let's say, a supermodel. Well, I'm not a supermodel. Let's say there is a supermodel. He is lean and he's about yay height as me. He's lean, he's not as heavy as me, but this gentleman is wearing shoes that have pointy heels. Even though he has much lesser weight than I do, if this guy steps on your toes, it would hurt. It would hurt real bad. You know why? Because his weight would be supported by very small amount of area under his heels, but I would be wearing shoes and my shoes would have relatively a large flat surface. So pressure is the distribution of force, all right? This tiny area, if this tiny area is present, it can have a large amount of force, all right? And if my weight is distributed over a large amount of area, the pressure would be very less, okay? Now there are certain dimensions of pressure which are ml minus 1 t minus 2. You can easily derive them by doing the dimensions of force, which are mlt minus 2, and dividing them by the dimensions of area, and you will get ml minus 1 t minus 2. There are certain units of pressures other than Pascal. 1 atm. 1 atm is the amount of pressure which is exerted by air column right above us, and that pressure is, please remember this value. This value is absolutely important. It should be remembered. I mean, no matter how much I stress upon it, this is definitely important. Okay? They might give this value to you in your exams, but I will still request you to remember it. It will fasten up your calculations. It's the same thing as 1.01325 bar, and a bar has this much amount of pressure. Okay? A bar has 10 to the power 5 pascals. 1 atm is also 760 mm of Hg. It means that if I have a column of mercury which is 760 mm tall, I would get the same pressure as the air column above us, and that is the same thing as 76 centimeter of Hg or 760 torr. You have to remember all these values. Now coming back to pressure. Why is it that pressure truly acts? My dear students, I would like to tell you that pressure acts because of molecular collisions. All pressure acts because of molecular collisions. You can see that there is this tumbler and there are so many molecules inside and they will be doing random motions. Assume that there is this particular molecule. It comes, strikes the wall, hits and goes back. Now, the direction of force will be perpendicular to this wall. It is very easy to understand this intuitively, but you can also understand this mathematically. How so? You can say that this has a certain velocity, let's say v, and this velocity has two components. One this One is this perpendicular component and one is this parallel component to the wall. And when it goes away, it again has two components. One is in this direction, which is perpendicular to the wall, and one is parallel to the wall. So you see that this component and this component, they remain the same, whereas this component and this component, see, this changes to this. All right. You can say that the component which is over here, P initial, is minus mv. Why am I saying that this is negative? It's negative because it is towards the left side. I have taken the left side to be the negative. And over here, the final one, I have taken this to be mv. All right. And what is the change in momentum? This is mv minus mv, and that becomes equals to twice mv. Okay, you see this change in momentum, it's only perpendicular to this wall, and that is exactly where the direction of force will be, as explained by Newton's law, Newton's second law, that it is the same as the rate of change of momentum. If this collision takes a very small delta t amount of time, then in that delta t amount of time, I will be sure that the force must be acting perpendicular to this wall, and that's why this is where the force acts. And what is pressure? Pressure is the distribution of the force, and the force is perpendicular, and that's why we can say that pressure causes a force perpendicular to the surface in contact. Okay, this is another demonstration of how pressure works. You can see that I have 300 Kelvin of temperature over here in this gas, and the pressure reading is 19.3. But this gas has a large volume, and that's why we can say that the number of collisions that are happening, each collision is causing a force, but those collisions are happening less frequently. And that's why we have a lesser pressure over here. All right. But over here, what I have done is that I have simply taken this and I've compressed this and I've made this container. So here we have more frequent collisions, and that's why the pressure is a lot more. This is 42.7 atmospheric pressure, while this is only 19.3 atmospheric pressure. And why is this happening? Why is the pressure over here more? It's because the same molecules over here now hit much more frequently. Try imagining it in such a way. Let's say you have a wall, but you have a gun, and this gun can shoot one bullet at one time, and it shoots like this. The amount of force that the wall will feel will be, let's say it's a bullet, so it's going to be quite intense. But instead of this gun, if I put the same bullet inside of a gun that can shoot quite rapidly, like ta 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 ta, ta like that, in that case, the wall has a serious chance of getting damaged, because now the bullets will be hitting the same point more frequently, and that causes a higher amount of overall pressure. Okay. Now, if we have a constant pressure value, then force becomes equals to pressure times area. If at all the pressure is variable, if pressure varies, then for overall calculation of force, we must perform a small integration. Integration of P dA. Please remember this, guys. This is useful. It will appear to you in many calculations, many problems later on. Okay. Star mark statement says that this force is perpendicular to the area. Parallel forces to the area are due to viscosity, and ideal fluids are inviscid. My dear students, what it means is that we will not consider forces that are parallel to the surface. We will only consider forces that are perpendicular to the surface. Viscosity is the reason why there are forces that are parallel to the surface due to a fluid. But we are going to take inviscid fluids, which means that our fluids are non-viscous, and that means no parallel forces along the area. Only perpendicular forces will act along. Here, if we talk about pressure in liquids due to collisions, you see, guys, I have taken a container. Okay? And in this container, I have a sphere. It's a hypothetical sphere. What I see over here is that in this imaginary volume, all the molecules will try to come and they will try to hit in this manner. Okay, so we can say that the pressure will be acting in such a way. All right, if I take a if I remove this part of the fluid and I replace it with something else which is spherical, okay, let's say I put a black colored ball in there. This ball is going to experience forces due to the collision of these molecules. Same thing, if instead of a ball, I put a block which is cubical in nature, this will experience forces in such a manner. All right? In such a manner. And all these forces, as you can see, are perpendicular to each of these surfaces. Now, this is a three-dimensional diagram. You can assume that in case of this three-dimensional diagram, again, the forces will be in such a manner. You see this front face will be pushed towards the back. You see the back face will be pushed towards the front. The left face gets pushed towards the right face gets pushed towards the left. You get the idea, right? So this is how all pressure acts, and all of this is because the pressure in liquids is due to collisions. Now let's begin discussing about the atmospheric pressure. So atmospheric pressure is, well, you already know what pressure is. It's the force which is distributed because of the presence of atmospheric gases up above us. And there are a lot of atmospheric gases like there's nitrogen, there's oxygen, and then there's a little bit of carbon dioxide and other gases. Now, all these gases, they are around us. And if you were to sit on a rocket and then you were to shoot yourself above in the rocket, then you will see that the gases persist for quite a bit of height. All right. And all these gases, they are full of molecules. These molecules, they hit everything around them. If there's an airplane at a very high altitude, these molecules would be hitting the surface of the airplane, causing a pressure. Around me, I see that, well, I don't see actually. There are air molecules, but yes, these air molecules must be hitting me from all the directions, causing a force on me. Everything around us experiences atmospheric pressure. So what is atmospheric pressure? It's the force which is distributed over a unit area in the presence of atmospheric gases. Okay. And as you go higher and higher and higher, you notice that it decreases with height. If you have ever gone into the mountains of Himachal Pradesh or Uttaranchal, those are like really high mountains. As a tourist, if you've gone there, there is one complaint that most tourists always make. You know what? It's because you can't cook soup so easily at the height of the mountains. You will try to cook vegetables and you will try to boil water, but the water will boil at a lower temperature, which means that you cannot give enough energy to your food, and that's why your food will not get cooked properly. It's because the atmospheric pressure at those altitudes is very less. So that's what you learn over here, that the atmospheric pressure decreases with height and it is higher near the Earth's surface. Near the Earth's surface around us, the pressure is much higher because the gravity pulls all the gases downwards. And as it pulls gases downwards, the pressure, the force with which they hit us at the surface of the Earth is higher. The pressure that they cause is higher. Okay. And that's the reason why it's easier to cook food near the Earth's surface, near the sea level, as it is compared to the mountains. However, the value of atmospheric pressure, do not underestimate the value of atmospheric pressure. It is a huge amount of pressure. You can see that if I have a can which I evacuate, okay, this can has a lid and I have taken out most of the air that I could. what I notice is that this can gets crushed because of the atmospheric pressure. See, what happens is that, you see guys, this vessel, all right, you see this vessel. In this vessel, there's a fluid, all right. There are molecules hitting from the top, and those molecules are giving a certain force to this fluid, and this fluid is trying to transmit this force onto the walls. From the outside also, there are molecules of the air hitting, so this fluid can bear the atmospheric pressure acting from the top and transfer the force over here, and this glass beaker does not really break. But what about this can? This unfortunate can has been crushed. And the reason is there were no, or maybe very less number of air molecules inside. They were not applying enough force from the inside, but from the outside there was a lot of force that crushed the can. And why was there a lot of force? It was because of atmospheric pressure. The air molecules, they hit it from this direction with a high amount of force, and it got crushed. Okay, so this image demonstrates how an evacuated soda can get crushed due to atmospheric pressure. And I would like to give you guys more examples. You play with Nerf guns. I don't have a Nerf gun right now, but I could show you if I had one. Nerf darts. If you shoot a Nerf dart on the wall, there are sticky darts, right? They go and they get stuck. Now they get stuck, and I'm sure you must have noticed that it takes a bit of force to pull them off, right? Because what happens is that they have those concave shaped paddings, and those concave shaped paddings, they go in there and then they get pushed. Now, there is no air underneath them. There's no air, there's only air outside of them. So that outside air pushes the Nerf darts onto whatever surface they're on, which is why it's easier to stick those Nerf darts onto smoother surfaces. On rough surfaces, it's a problem because air can get through from the sides, all right? But on a smooth surface, it gets stuck perfectly. And this is exactly the principle that is used by reptiles to crawl on walls. What they do is that they hold the surface like really hard, and then the atmospheric pressure keeps their puts a large amount of force on their feet, and that's how they're able to stay stuck on the wall. I mean, you can't do that because, well, your hands are not designed to create that sort of a suction pressure, that sort of evacuation. But yeah, some animals can do that. Okay, and that's why they are able to crawl on top of the walls. That's actually the fact. Okay, and this atmospheric pressure is 1.01325 times 10 to the power 5 pascals, as we have already discussed. And you see, guys, this amount of force is equivalent to 1,000 kg mass that is kept on a 1 meter square area. It's a large, huge amount of force. Now, you see that I am able to lift my leg because my leg is not stuck to the ground, obviously. However, if I were to use those sticky concave Nerf dart heads underneath my foot, and I would stick my foot onto the floor, I would have a lot of difficulty lifting up my foot. You know why? Again, the same reason. It's a large amount of force. It's a very large amount of force. Even if I were to use smaller area, like perhaps a tenth of a meter square, a tenth of it, I would still be having to lift 100 kgs of mass. That's just a lot of mass. I can't do that with one leg, right? I mean, perhaps some people can who are really fit, but yeah, not me. So, density of air. Dear students, the density of air in our nearby surroundings is assumed to be constant, and that's why we will not consider atmospheric pressure to vary. I would like you guys to remember that the atmospheric pressure has a fixed value. It is 1.01325 times 10 to the power 5 pascals, and that is what we will always take it to be. Let's now talk about the most important part of today's lecture. I mean, everything is important, but like up until now, it was a built-up. Here, we are studying about pressure in liquids. So, my dear students, liquids cause pressure. Well, how do they do that? Now, you see, guys, that if I have something like this beaker, okay? If I have something like this beaker, and I have fluid filled in it, okay? Let's take this fluid and fill inside of it. I mean, I can't make it as colorful as this beautiful image, but yes, let's just assume that there is fluid filled inside. What I'm going to assume is that this fluid is made up of many hypothetical layers. Okay? These layers are kept on top of each other. Imagine having a stack of books. One book, another book, another book, another book, another book. Stacks on top of stack of books, books on top of books on top of books. Your hand would feel a lot of force. Okay. But now, what do? Take some books, put on one hand, and then put the other hand in the middle of the stack. This hand would be feeling less weight because there would be fewer books on top of it, but this hand would still be feeling a large amount of force on it. And the reason, like I said, is all pressure is caused due to molecular collisions. Gravity pulls down the molecules over here and then makes them fall right underneath. And as they fall down, they hit with a harder force. And that's why at the bottom, there's more pressure compared to the top. And by what amount is this pressure present? We are going to learn over here. Let's assume that this is a hypothetical section of liquid. This is liquid, okay? This is not solid, this is liquid. This is a hypothetical, like you can assume that this whole thing, okay, this whole thing is like enclosed in some container, okay? And this is a part of the liquid, and I'm only studying this part of the liquid, all right? I'm only studying this part of the liquid. Like I'm only studying this portion. And this is all made of liquid, all right? Now, what I can say is that if this is a part of the liquid which is in equilibrium, the net force acting on this must be equal to 0. That's exactly what is meant by equilibrium. Equilibrium means that the net force acting on anything must be equal to 0. Now, if we draw the free body diagram of this, which is what I've drawn over here, I will see that there is a P1A force acting from above. Because you see, I had enclosed this in a liquid and it was like all full of liquid like this. All right, it was all full of liquid like this. There's also liquid underneath, but I'm not showing that. I'm just showing you this liquid so that you can see that it is this liquid which is applying a pressure on this above surface area. And this pressure is P1. I'm assuming the value of to be P1. The area is A, and that's why the pressure downwards is simply P1A. Okay. Now, I had assumed that this is like entirely enclosed in this container, all right? And now there is liquid completely over here too. Okay, there's liquid like this. There's liquid like this. Now, this liquid is again, this portion is pushing our hypothetical piece of liquid from underneath with a force of P2A. All right. So the net force that is acting must be 0, right? So there's an upward force. All right. There's an upward force there, and then as in like force on the upward surface, which is in downward direction. Force on the lower surface, which is in the upward direction. All right. Now, in order to support this weight, you see this weight which is mg. In order to support this, what must be the logic? The logic must be that the net force due to pressure, which is P2 minus P1A, should be equal to the weight. All right. To support the net downward force, which is P1A and mg, which is what I've written over here, the upward force P2A should be strong enough to do that. Now, if I solve for this, if I take P2 minus P1, which is the difference of pressure, comes out as mg upon A, as you can see from this equation. This A area goes underneath this and becomes mg upon A. This P2 minus P1 then becomes mg. And what is m? M is the mass of this fluid. All right, m is the mass of our fluid element which we have taken. It's the part of this. Now, this mass has to be equal to the density times the volume. For those of you who do not remember this small idea, I'll just write it over here that, well, mass can be assumed to be the product of density and volume. Okay, mass can be density times volume. Now, what is the volume? You see the volume of this, is the area times the height. Do you see that? In fact, we'll take this over here for a moment. Now, this volume is actually the area times height times, well, the g is just there. G is the acceleration due to gravity. And then we cancel the area, and that, you see, rho hg is then written as rho gh. Okay, and that's what I have written over here, which is the first thing that we learned on this page, that the difference in pressure between these 2 points depends only on the height. All right, it depends only on the height. Delta P is equals to rho gh. You see now that density, again, we are going to assume it to be constant. Okay, but it is possible that density, all right, density can have all these different sort of variations. Then what should we do if density begins to vary? In that case, guys, which is, well, never going to happen in your syllabus, but just in case, if that happens, then you are going to have to use a little bit of integral calculus. Then you're going to have to use that the density should be a function of the depth, all right? So rho dh is supposed to be integrated from h1 to h2, where h1 is the height of the first point, h2 is the height of the second point, and you're trying to find the difference of pressures between these 2 points, and that's why it is g times integration of rho dh. But guys, again, this, a varying density is not likely to come in your exam, because they have explicitly said that we assume the fluids to be incompressible. Now you see that this is for compressible fluids, and this P2 minus P1 is rho g h2 minus h1, which is what is going to be the useful part for us. This is the most useful thing for you. Please note this. Okay. In regular situations, what you will see is that if I have a point underneath the fluid, let's call this point 2. At this point 2, the pressure will be equal to the pressure because of the atmosphere from top and due to the pressure due to the liquid. The pressure due to the liquid will be simply rho gh, and the pressure due to the atmosphere will be PATM, and that's why the pressure at any point is defined by its depth, by how deep it is. H is the depth underneath, all right? I have not used the symbol D for depth over here because some people will then confuse it for density. Density is specifically written with rho, and I have omitted the usage of the symbol D because sometimes in calculus the symbol D appears. That's why H is most commonly used over here. And this point 2, where we want to calculate the pressure, we get interested in how deep it is from the surface. That is multiplied by rho g to find the pressure only due to liquid, and then added with PATM. Okay. So this is exactly what I've explained over here, that pressure at any point which is at h depth from the surface is P naught plus rho gh, where P naught is the atmospheric pressure. Rho gh is hence the pressure due to h height of only the liquid. All right, only the liquid. Rho gh is only due to the liquid. All right. If you were to draw the graph between pressure and height, you would see that you would get a straight line, and the slope of this will be tan inverse of rho g. Okay, this kind of resembles y equals to mx plus c. Okay, you can see that this equation is like, you can write it over here, that this p equals to rho g h plus p naught, which is our standard equation, kind of resembles y equals to mx plus c. All right, where this c is the intercept, this is the p naught. Okay, and then the slope of this graph is rho g. That's why I've written tan inverse rho g equals to theta, or tan theta equals to rho g, and this x is on the x-axis. We have the height, as in like the depth from the surface. This is the part which I would like you guys to be interested in. Please do not commit the most commonly committed errors by students. In my experience, I have taught for many years and I have seen students committing many kinds of mistakes. And that's why I wanted to put these out there for you guys. In case you commit these mistakes, omit them. And first thing that you should omit is that you think that fluid pressure is rho GH. Guys, fluid pressure is not rho GH, it's P naught plus rho GH. Okay? Especially if the fluid has a free surface and the surface is exposed to the atmosphere, then the fluid pressure is P naught plus rho GH. It's not simply rho GH. Okay? It's the pressure difference which is rho GH, which I have written over here. You see on this page, here, it's delta P. Guys, please notice that it is P2 minus P1, which is delta P. It is not P. P is actually written on this page, which is P naught plus rho GH, PATM plus rho GH, okay? Now, some students can possibly take the height from the ground. Again, big mistake, don't do that. Height is always taken from the surface. It's actually depth, but we mention it with H. They think that pressure has a direction. Pressure does not have a direction. I cannot stress this enough. Force has a direction. Pressure does not have a direction. And sometimes students think that pressure can only act vertically. But again, guys, that's not the case. Because let's say if you have a wall over here, all right, and fluid is filled over here. What about this wall? Will this wall experience only a vertically downward force? And the answer is no, a resounding no, because the force will be acting in this way on this wall. Okay, this will be the force acting on this. In fact, these forces will be different because as you go downwards, the pressure will increase, and as you go downwards, the force on this side will also increase. So if I write this as F2, F1, F2, F3, and F4, then I can say that F1 will be much bigger than F4, and in the middle of that, you will have all other values. Okay? Is that fine? I will remove this now. This was only for the explanation part. If you want these slides, if you like these slides, then you can always contact me and I'll just give them to you. I'll just give these slides. Okay, so now let's talk about something called the beautiful hydrostatic paradox. Hydro means water and static means stationary. Hydrostatic means when liquid is stationary. Paradox. What's the meaning of the word paradox? Paradox means a confusion. Paradox means, well, something that there is, but you don't really see it. And the most surprising paradox that I've seen in my life is circus jokers, the jokers that perform in circus. Well, they are very sad people. They make everybody laugh, but inherently they are very sad. Now, this is a paradox. Similarly, check this out. You see that there are all these different kinds of vessels. This vessel seems to be like the thickest of them all. And still, pressure on the same horizontal level is the same. Even in this weird looking shape, the pressure is the same over here as it is over here. A large amount of water seems to be present over here. Still, the pressure is same. In fact, over here, this has a very low area and still the pressure is the same. I mean, we did discuss about the supermodel, right, who was wearing heels. And even if there is less mass but very tiny area, P upon A, very small denominator should give us a very large pressure. But no, you have the same pressure everywhere. And that is the hydrostatic paradox. You see, they all have their free surface at the same level. They all have atmospheric pressure acting on top of them. And at this depth of H, they all have the same pressure, P naught plus rho GH. Okay? That's the paradox. And that's what we are trying to resolve over here. You see, guys, there were many experiments that were done by this amazing scientist. His name was Pascal. And I will tell you about Pascal's law in the next lecture. This is a nice setup that Pascal had actually put together. And we'll now try to understand what is happening over here. You see, that this is a vertically oriented liquid column. This is a conically oriented liquid column, but the pressure over here and over here is the same. In fact, this has a very tiny volume, and still the pressure over here is same. So clearly, the amount of water does not matter. The amount of liquid does not matter, right? This one has a lot more liquid. This one has a lot less liquid. Still, the pressure at the bottom are the same. Now, the force required, okay, the force required to balance, let's say, if you see this diagram, check this out. Now, this has a different shape. Now, there is a mass kept over here. What I have done is that I have taken this mass and I have put it on a weight balance. And I see that the weight balance which is required over in this sort of an orientation was the same in all these three of them, because pressure only depends on the height. Now you must be thinking, sir, but why? Why is it that the pressure is depending only on the height? To that, guys, I would say that just look at the situation of this conically shaped vessel. If I were to draw a hypothetical line over here, you will notice that there are all these forces acting that are supporting the liquid which is on the side. This surface is only supporting this liquid. Very similar to this surface, supporting only this liquid. The remaining liquid is supported by the side walls. And then you will say, but sir, there is no liquid over here. Then how so? And to that, guys, do you see this tiny part over here? Very tiny part over here. If I were to poke a hole in this, you will see that the fluid will pop out like that, which means that the fluid must be hitting this surface. Let me draw the surface over here, this tiny surface. The fluid must be hitting this tiny surface from the inside like that. Now, according to Newton's third law, this surface would be applying a force in this direction, which means that the force which is absent due to the absence of the liquid in this region is now put because of this tiny surface. All right, this tiny surface, they are trying to apply a force downwards. And that's the reason why the pressure over here is compensated. Okay, and that is the solution to the hydrostatic paradox. All right, you see, pressure is a fascinating quantity. This is, well, a smoke. It's a smoke cylinder. Okay, and this is a cylinder in which the smoke is being pushed downwards. But can you see that the smoke is coming out of here and here and here equally? Because there are three holes over here. But this is smoke. This is not liquid. If this was liquid, you would notice that the liquid would be coming out of this hole a little faster, because this one has more pressure, this one has less pressure. But because this is smoke, smoke is what? Smoke is gas. They are all coming out with the same, in the same manner. Okay, so pressure in liquids behaves slightly differently from pressure in gases. In gases, you see the pressure over in the overall sphere over here would be the same, but the pressure in this case would be increasing as you go downwards. All right, if I were to go at this depth, and let's say this is H1, the pressure over here will be P naught plus rho G H1, and the slanted height does not matter. If I were to go at this depth, let's say this is H, then the pressure would be P naught plus rho G H. Now you see, guys, why is it that giraffes that are taller than elephants, and I'm certain that elephants have a lot more weight than giraffes. They are like big and bulky. Giraffes have a thicker heart. You can't break a giraffe's heart, right? It's thick. It has thicker muscles. And why is it like that? It's because giraffes are the tallest creatures among all living beings. I mean, in animals, there are there are trees, well, but you see again, trees, the taller the tree, the wider the trunk, right? Now, that's the general case. But giraffes have a very thick heart because it's supposed to pump a lot of liquid, a lot of blood to his brain. And his brain is at a very, very large height. So it has to have a very thick heart. A giraffe's heart is thicker than the heart of an elephant. Okay? And for good reason, because pressure only depends on the height. And that's the answer to the hydrostatic paradox. Okay? Now you see that if I have a glass vessel which is like yay big, and I take a very tiny capillary, and I have this capillary like a very small PVC tube, maybe to 3 or 4 stories of a building, and I start pouring water from top. Do you know what's going to happen to the glass vessel? Even if I pour in that capillary, if I pour barely 1 liter of water, that vessel is going to break because pressure only depends on the height. Okay. Now let's talk about pressure in a vertically accelerated fluid. You see, guys, that if I have this vessel which is kept in a vertically accelerating lift, then instead of difference in pressures being equal to rho gh, I will have rho g plus a times h, where a is the acceleration of the lift. This happens because, again, we analyze everything in fluid statics with respect to the container, in the frame of reference of the container. And the frame of reference of the container, the g, which is usually acting downwards, now becomes g plus a, and this is called the effective g. Okay, this is called the g effective. And similarly, if I have a container going downwards in a lift, then this becomes rho g minus ah. Now this is again very fascinating, that if I have a freely falling fluid, then the effective downward acceleration will become 0, and that's why pressure does not vary with height in liquids that fall freely. Okay, you see that the liquids that fall freely, in those you do not have pressure varying with height. Check this out. The world's tallest building, the Burj Khalifa. Take your time, read the question. It says, how does the pressure vary in a liquid filled container which is thrown off the Burj Khalifa? Now, if I take a liquid container, okay, and if I throw it off of this building, all right, and this is falling down, it's going to take a while to fall down, right? While it is in the air, what do you think is the pressure in this falling container? The pressure in this falling container is not going to vary at all. It's going to be P naught. And the answer to this is that the pressure will be equal to P naught everywhere. P naught is atmospheric pressure. It will be equal to the atmospheric pressure in all cases. But you can then say that, sir, there will be some surface tension. Yes, there will be surface tension. We can include that, but for now, let's ignore it. But fact of the matter that only gas is going to act, and only gas is going to give it pressure. Because of the height, it will not have any pressure. Imagine this way, that if I have a stack of books, okay, now I put this stack of books on my head and I jump off the Burj Khalifa. Yeah, imagine I have 9 lives, okay, I'm not going to die. With a stack of books on my head, and I jump off Burj Khalifa and I land safely, okay, hypothetically. Is this stack of books on my head going to put weight on my head? Not at all, right? That's the same reason. So if I have a liquid container falling, freely falling in gravity, it will not have any pressure. Let's take a look at this question. What is happening over here? He's asking you to find the pressure at the interface. Well, we can easily see that the pressure at the interface will be P1. There is only rho height on top of it, like rho liquid on top of it for an H height. So we can P1 plus P naught, P1 equals P naught plus rho GH will be the pressure. No doubt about this. But the second part of the question, you see, is asking pressure at the bottom, as in over here. We have liquid filled with rho height, H height for a density of rho, and another liquid, H height, density 2 rho. What's going to happen? We will now have pressure due to both the liquids. There will be atmospheric pressure P naught, rho GH due to this liquid column, 2 rho GH because of this further liquid column. I have given you the values of density rho, area and H. You can put them and you can find out that the final value of pressure at the bottom should come out to be P naught plus 3 rho GH. All right, should come out to be 3 rho GH. This question, take a time, read this question. What does it say? He's asking you to find the force due to pressure at the bottom. He's also asking you to find the weight of the liquid, and he's also asking you to find the net force by the liquid on the walls. What do we have here? We have a frustum. Okay, what is a frustum? A frustum is basically just a cone which has been chopped off at a certain height. Okay, this frustum has a height of h. It has a bigger surface over here which has a radius of 2r, smaller one over here which has a radius of r. Okay, now what shall we do? Let's solve for the first part. Force due to pressure at the bottom. My dear students, what is the pressure at the bottom? It's P naught plus rho GH, isn't it? Okay, we've just studied that pressure only acts because of the height. So it's P naught plus rho GH. What do you multiply that with? You simply multiply that with the area. With the area that is over here. And what is the area? Area of this circle is pi r squared. And that's it. That's your answer. P naught plus rho GH times pi r squared. What's the second part? Second part says, find the weight of the liquid. Okay. Again, that's easy. We can do that. Weight of the liquid is what? mg. M is the mass of the fluid which is inside. Mass is density times volume. And the volume can be found using this standard formula. If you do not know this formula, please note it down. 1 upon 3 pi r1 squared plus r2 squared plus r1 r2. This formula is very similar to the formula of a plus b whole squared, except for here there's a 2 missing. Okay, it's pretty much the same, but the 2 is missing. So it's just r1 squared plus r2 squared plus r1 r2. And h is the height. Now you can just put the values of r1 and r2. They are given to you as r and 2r. And when you put them, you get 7 by 3 rho pi r square hg. Now this is the weight of the liquid which is acting downwards. All right. Now, my dear students, the fact is that this weight is going to be supported by what? What is this weight going to be supported by? It's going to be supported by the walls of the container. Okay, this pink arrows, they show the force which is applied by the liquid on the walls of the container. And Newton's third law says that the liquid will also experience the same force because of the walls of the container. Okay. The horizontal component of F2 gets cancelled. This F2 is acting in this direction. Okay. This will have a component over here and this will have a component over here. So this force will have a component on this side and this force will have a component on this side. So you see this component and this component, they get cancelled. We only are left with the vertical component of F2. Okay. So this F2, okay, if I write the vertical or not, it's pretty much like it makes the same sense because F2 is basically the total force acting downwards. This force F2 plus F1, that should be equal to mg. Now what is F1? F1 is the force which we found out in the first part. Okay, the force acting, this one, this is F1. Okay, now this force is what is acting on this in this direction. So the container is also supporting it with F1. You see, F1 is basically the force. It's basically the force which is due to the liquid column directly above this area pi r square. Okay, this area is pi r square, and the liquid column directly above it, this liquid column will have this certain weight. Okay, and to support this liquid column, we will have F1. All right, the rest of the force is just simply F2. Okay, so you get F2 plus the weight of this liquid column, which we have found out earlier, that should be equal to mg. And if you calculate F2 from here, you get this value. You can also argue that, sir, if I remove this cylindrical column from the volume of the frustum cone, and whatever volume I am left with, if I calculate the mass of only that volume, will I get the same answer? Yes, you will. That would be good thinking. Okay. Now let's do a little bit of another problem. I would like you guys to take some time, read this question. So let's take a quick look at what is happening in this question. We have a submarine that is experiencing a pressure of 5.05 megapascal. My dear students, 5.05 megapascal is the same thing as 5.05 times 10 to the power 6 Pascal, because this is exactly what a megapascal is. Capital M is mega. Megapascal is the same thing as 10 to the power 6 Pascal. Okay, please remember this part. Similarly, it is given to you that there is another point which is experiencing 8.08 into 10 to the power 6. Now you see guys, this is a small error, and this should have been written like this, 10 to the power 6. Okay, so this is 8.08 megapascal. So let's call this point P1. P1 has this pressure, and P2 has 8.08 times 10 to the power 6 Pascal pressure. Now you see guys that P2 is equal to rho G D2 plus P naught, and P1 is equals to rho G D1 plus P naught. And P2 minus P1 should only give us rho G D2 minus D1. All right. So if you subtract these two values, then you will see that this is 8.08 minus 5.05 times 10 to the power 6 Pascal becomes equal to rho G D2 minus D1. In the question, he asks us what is D1 minus D2, but obviously he's asking about the magnitude. So D2 minus D1 and D1 minus D1 minus D2 are practically the same things. One more small error in the typing of this question is that there should have been a 10 to the power 3 kg per meter cube for the density of water. Okay, now you see, if I calculate this, it's just going to give me 3.03 times 10 to the power 6, and rho is 10 to the power 3, G is another 10, and you get D2 minus D1 over here. And if I solve this, you see these powers of 10, they get cancelled, and I simply get D2 minus D1 equals to 303 meter. Okay. And what is my closest answer? My closest answer is option A. You see, this is a JEE PYQ, guys. So these kind of questions, if they can appear in JEE, they can appear in JEE again. These kind of questions can also appear in NEET. They can sometimes copy direct JEE questions into NEET. So let's just do a quick one more question before we wrap up this lecture. We have a lake. All right, we have a lake. Okay, let's say this is a lake, and it says that there is a certain pressure at depth D, and there's another point at D by 2 where there is certain other pressure. So let's call this point P1 and let's call this point P2. So he's saying that the pressure at the point 2 is 2/3 the pressure of the point 1. All right, no problem. So we will just write the values of pressures at this point and this point, and pressure at P1 will be rho G D plus P naught. Okay, this is the pressure P1, and that is given to you as 2/3 of the pressure at this point, which is P naught plus rho G d by 2. Well, I guess this 2 by 3 is here, right? Because this pressure is 2/3 of this pressure. Yeah, this is more correct now. So the 2 by 3 goes over here. So let's solve this. It becomes 2 by 3 rho g d plus 2 by 3 p naught equals to p naught plus rho g d by 2. Okay, I'll take the like terms on the same side. It becomes 2 by 3 minus 1 by 2 rho g d, and that is p naught minus 2 p naught by 3. Okay, and if I solve this, what do I get? I get p naught by 3 equals, you see, p naught minus 2 p naught by 3 is p naught by 3. Okay, 1 minus 2 upon 3 is 1 upon 3. And what is this? 2 upon 3 minus 1 upon 2 is rho g d upon 6. So I get d equals to 6 by 3 rho, p naught upon rho g. So this is going to be 2 times. P naught is, well, technically close to 10 to the power 5 Pascal, and rho g is, as we saw in the previous question, 10 to the power 4. And my depth is now 20 meter. Okay, so my correct answer is option B. Okay, so these kind of questions you can see in fluid statics. Okay, the pressure related questions. In the next lecture, I will be teaching you about barometers, Pascal's law, like I mentioned before, and horizontally accelerated fluids. Now, this is where it becomes really interesting, which we will discuss. And then the further application is in rotating fluids, and we will do some more practice questions on that. So, guys, I hope you enjoyed today's lecture, and I will see you in the upcoming lecture with all these new and amazing topics. And stay tuned. And until then, get physics rich.